Test. Test 1, 2, 3. Okay, hope this is gonna work. Pay attention about the bandwidth, capacity, the link, the access network's transmission rate, the bandwidth. And all the homes. So typically hundreds of homes will be connected through one cable distribution network to the cable head where the routers are, the servers are, and where the internet is connected to. And this shows how each of us is connected at home to the cable network. So we do have here the PC generating data. How it works is that the data reaches the cable modem and it gets modulated, translated to signals that the cable TV can understand. So this side here might taking control signals where maybe your parents are switching from TV program to another TV program, and it get merged here and sent out. And this is going to go through the distribution network to the cable head. And cable head here is going to reach the internet, and the server sends something back, and back here the splitter here split the signal. TV program shows go this way, and internet data coming back this way. And the modem here is going to demodulate it and then send the data back to you. Now, what's amusing is that, hey, therefore, on this cable distribution network, on this cable here, we are modulating all sorts of contents like video, data, as well as some control signals. So what really happened is, oops, all right, good, it's time. Let's start. I hope this is working. Now let's go to the part that we are left off last time. Interesting. Oh, I lost my handle to the OBS, the streamer. Oh, there we go. It's back. Yeah, let's see. lecture. Good. Okay then. This is where we are left off. Access networks and physical media. There are actually several types of networks. Last time we covered just one called the ADSL. Okay. Now, there are typically three kinds of access network. First is the residential access. Second, the institutional access. So institution over here. Residential access over here. And the last kind, mobile access network. But this is actually to categorize them by what the functionalities of the organization is. So this is typically a company, a university, and this is household. And this is, we moving around carrying smartphones or mobile devices. But each of these access network could be using different kinds of access network technologies. So we'll talk more in the next few slides. Now, just keep in mind when we're talking about these access network technologies, pay attention to the bandwidth provided by these technology. As we go on, as the technology gets improved, usually the bandwidth goes higher. Now, some of these access networks share physical cables. Therefore, for example, households will be sharing the entire bandwidth. That means when other people are using, one of us is going to suffer. Now, if the technology uses dedicated connection, dedicated cable, that means that you will be just using the entire bandwidth. That gives the users a certain advantage. So pay attention to bandwidth as well as where the cable or the connection is shared or dedicated. So this we talked about already, DSL, which is also often called the ADSL. Okay, what it does is simply that, let me go back. What it does is simply to modulate signals from home machine right here and convert it to analog such that it can be merged with phone calls and goes on the ADSL cable to this thing, central office. At this box DSLAM, it's going to split. The data goes this way and voice go this way. Okay, so what's amusing here is at the ADSL cable, phone calls as well as data going upstream to the internet and data coming downstream to household are modulated onto the cable, but using different frequency bands. So voice here, and this is upstream, and this is downstream. So you see that there's a differentiation between the downlink bandwidth as well as the uplink bandwidth. So downlink here use a wider band, can send data up to 5 megabits per second. And the uplink, using a narrower band, uses only 1 megabits per second. Okay. And the dedicated, this is using a dedicated line. So this here is dedicated per household, per ADSL user. Now, the second type of access network technology is called the cable modem. This is, again, used a lot by home, okay, by households. So what it does is, hey, instead of using the telephone infrastructure, how about we use the cable TV? Yeah, because we also have a huge cable TV network, and the cables are already built in, some underground, some above ground. So cable TV was also there before internet. When internet shows up, when the home computer wishes to connect to the internet, some of us thought about connecting it through the telephone infrastructure, that is ADSL. And some other of us thought about, hey, use the cable TV infrastructure. So that's where cable modems came from. Now, what's slightly different is the cable being used by the cable network is this. It's a hybrid cable where you see a bit of fiber and a bit of copper. Some segments uses more fiber, some segments uses more copper coax. The link is also asymmetric. For downstream, 30 megabits per second. but for upstream, only 2 megabits per second. But generally speaking, the bandwidth is much higher than the ADSL. And most of these homes, and it could go up to hundreds and thousands of these homes, it will be connected through a cable distribution network to the central office. Okay, what's very different of the cable modem access network to the ADSL is this. The homes connecting to the same distribution network will be sharing the bandwidth, okay, all the way to the router. So ADSL has a dedicated access, but cable modem here, although higher bandwidth, but it's shared access. So let me illustrate. Households are here. Oops. Let me go back. Sorry, that's not what I want. Go back one animation. There we go. Okay, so this is a household. Okay, individual homes. And there could be hundreds or thousands of them connecting to each other. And then through the, sorry, not working very well. Connecting through these cable distribution network to the central office. And this is where the servers and the routers are. The internet is going to be up here, over here, the internet. All right. And if we zoom into an individual household, we see this, computers wanting to connect to the internet over here. Very similar to ADSL modem, so data goes here, and this guy here, cable modem, works like a translator, translating the data signal to the signal the cable modem can consume. So your parents sitting in the living room watching TV could also be flipping channels. In that case, some control signal will go this way, and they get merged here, and it go all the way through the distribution network to the central office. Similarly, there's also a splitter here, differentiating whether this is a request for a TV program or this is a request that goes out to the internet. And similarly, internet sends something back, and TV program will also come back, and it travels the other way around back to the splitter. And TV program go back here, and your data come back here. All right. Now, what's a bit amusing is this. You heard, hey, TV program, control signal, data, they all go kind of just on this distribution cable. Yes, they do. What happens there is that on the cable, we're using a range of frequency to try to modulate the signals. So video here, data here, control here. They are actually using different sub-range of the frequency range. So channel 1 here is 1. So there are actually several, 9 of these sub-ranges, and we call these sub-ranges the channels. So video 6 here might be using, video 6 here is using a higher frequency sub-range, and video 1 there is using a lower frequency sub-range. So that was cable modem. The next one is fiber to home. I think it's actually more fashionable these days. You see, we use fiber to home, or FTTH, okay, to connect to the internet. Unlike cable modem, unlike ADSL, mostly we're still using the copper wires. This time we're using these, the optic links, and it goes from the central office to household, and all through the optic fibers. All right. So internet here sends data over at OLT. This is optical line terminal. So the row of this is almost like the merger and the splitter we see in the central offices for the cable network, for the DSL network. And it's going to translate the signal such that it's good to propagate over the optic fibers until it reaches home. So this is the optic network terminal. But OLT, ONT, whatever it's called, what it means are just terminals. Okay. end of the HTT home access network. Right. Now, what's a bit tricky is this. So FTTH access network has sort of two different grades, and it depends on how the optic splitter here before the household operates. Because data comes here, and this optical splitter here will try to identify exactly which household is the data for. So it's gonna be doing the routing. But some of them is also going to do the amplification. So as signal traverses a long way, it gets a bit weaker as it goes. So optic splitter here sometimes will amplify the signal before it propagates on the signal. So that kind of optical splitter is called an active optic splitter. It's powered, so the signal gets properly amplified. Now, some of these optic splitters are passive. It's not powered. It's installed with simply some sort of mirror and reflect the signal over, such as reaches the rightful destination. So that is called the PON. These days, we're seeing more and more of these AONs in place at these places. All right. And the FTTH operates at a much higher rate, hundreds and megabits per second. And it's now also carrying TV programs and phone calls. So very fashionable access technologies these days, FTTH. The next one that's commonly used is Ethernet. Pretty much all of you know about this one. Many of the big companies' institutional networks use Ethernet natively to connect. So company computers or university computers connected straight using Ethernet, and it connects to the institutional router and straight to the internet. So we bypass any kind of modem really. And the bandwidth much higher, 100 gigabits per second. This is like average, and maybe slightly below average. We're seeing 100 gigabits Ethernet switches these days. All right. And the last kind, wireless access. Although the bandwidth of wireless access is not much higher than the Ethernet, not much higher than fiber, but it's getting popular as it's more convenient to use as we move around. And one characteristic of the wireless access is that because we are sending signals, modulating signals on the air. So the medium is definitely shared. All of us sharing the space here share the bandwidth. So the most popular one is called the Wi-Fi. Okay, this is the wireless equivalent of the Ethernet. And the bandwidth goes up high to 54 megabits per second for AO211BG. But now we have AO211A something. So potentially the bandwidth can go up to hundreds of megabytes and sometimes gigabytes. And the other very popular kind of wire access, we call it the wider area access. But that is just a more sort of academic name for 4G. Okay? And this is provided by the telco operator. It goes up to megabits, and these days, tens of megabits. In the States, they are also called the cellular system. Okay? But in the rest of the world, 4G or LTE is a more popular name. And next, well, actually this year, some are forecasting that the second half of this year, we're going to see 5G showing up in certain regions of the world. Well, but I'm not sure. Maybe with the COVID-19 situation around, the development of the 5G might slow down a little bit. And the network looks rather different from all these other wired access network technology. It looks more like this. We're having a base station, and all the computers are simply sharing the airspace, and as they're transmitting, receiving wireless air signals, we communicate. So there's no physical cable connecting them in a way. Now, to sum up access network, what have we seen before? Before this slide. ADSL, cable modem, fiber to home, Ethernet, and then wireless access. If you observe the home network that you have, you might see something like this. Okay, you sitting here or here. In case you're moving around with the laptop without a physical Ethernet connection, you are using the wireless access network technology. If you are sitting on a desktop and it's connected through Ethernet, you are using this access network technology. Now, you might have a home gateway connecting all the home devices, but there is a cable modem that allows you to connect to the internet. So you are also using a cable modem, a residential access network technology here. So in a household, the home network oftentimes uses a combination, okay, of the access network technologies already. So this component here meant to indicate this guy here. There are more times being called a home gateway instead of being called a router or firewall. Okay. So that was access networks. Next, physical media. So this is to talk a little bit lower layer. So access network is like here at about link layer, and physical media is further down at the physical layer, where we talk about the very basic unit of communication, the bits. A bit is a byte. Okay, and if we talk about bandwidth, is always talking about how many bits we can transmit per second. So essentially, at the physical layer, all we care about is to propagate these bits, okay, from the transmitter to the receiver. So there's often a physical link that connects the transmitter and receiver. Sometimes wireless links, okay, connecting the transmitter and receiver. For the wired one, in the textbook, we also call it a guided media. The wireless ones are called unguided media instead. So let me introduce a few of these media that we use to connect the transmitter and receivers. First is the twisted pair. Well, I have to admit that this is almost a legacy technology, except that some of the Ethernets are still using twisted pairs. So what it looks like if you cut the old Ethernet cables and look inside, pull the copper wire out and look, you will see that it's actually two copper line twisted regularly across each other. So it's two insulated copper wires twisting each other. In the older times, we use the Cat5 category 3 cable, but this is very, very old for the very classic 10 megabits per second Ethernet. These days, some of you might still be using the Cat5 cable, but I think most of us are now using Cat6 Ethernet cable. Okay. Telephone wires is also twisted pair. Okay. And the next one is this, coax cable. This is still copper. The way it's bundled into the cable, into the insulate is this. It's actually two layers, concentric, one around another, sort of one within another. So looks more like what the picture is showing here. Okay. So the cable modem's cable, if you cut it open, it looks exactly like this. The transmission goes bidirectional, and it operates at two models. One is the baseband mode, the other is the broadband mode. Okay. In the older time, some of us is using such a cable to do Ethernet transmission. It has only one channel on the cable, so you can expect that the transmission rate. The bandwidth is very low. But most of us is using the broadband mode of coax cable. So cable TV is operating at this mode. So that's why you see HFC here. So there are multiple channels, as I tried to explain earlier, right? Optic cable network or copper cable network. It modulates data, including video, including data, including control signals on a frequency range. And we cut them into channels. Some videos go on some channels. Some data goes on some other channels. And for the FTTH, we use the optic fibers. So there are glass fibers essentially carrying light pulses. Each pulse is a bit. They operate on very high speed, okay, and mostly just point to point. Unlike Ethernet, it could be multi-point to multi-point. Therefore, the transmission goes really, really high rate, hundreds of gigabits per second. Now, in the backbone of the internet, some of these optic fibers operate even at higher rate, at the terabits per second speed. So one characteristic of the optic fiber is that it's very low error rate. There are repeaters, remember AON, the active splitters. They can amplify signal. Therefore, potentially we could have the same signal transmitted far and in good quality, okay? And therefore immune to electromagnetic noises. The last kind of media is radio. It's the wireless kind. In this kind, unlike the previous ones, we modulate signals on electromagnetic waves that rides on the physical cable. But this time, we modulate the bits onto electromagnetic waves that just kind of, vibrates the air, okay, vibrates the particles in the air and gets transmitted. Okay, so the signals got carried, okay, in electromagnetic waves. There are no physical wires. It also goes bidirectional, but you see, a wireless media here goes on the air. Although we could send things both direction, but the thing is that if we send them simultaneously, we're also sharing the air. They will potentially interfere with each other. Okay. So, hey, unfortunately, wireless access network technology using the air is more vulnerable to the physical characteristics of electromagnetic waves over the air. It will interfere with each other. And there are some other environmental effects. For example, if we are sending signals on the higher frequency band, those waves are easily obstructed by objects. Okay, they don't penetrate objects all that well. And we do have reflections here and there. And this could be potentially a headache because sometimes the transmitter's own signal gets reflected, and at the receiver, it's actually hard to tell what's real and what's really background noise when there are multiple copies of real signal that's coming in as well. See, so wireless links therefore does not carry that high the bandwidth like the fibers, like the coppers. Now, there are several radio link types. It depends on the frequency band it's using to modulate the bits. The most commonly seen one is this, the Wi-Fi. Okay. And then the wide area. So Wi-Fi operates around 2.5 gig, and nowadays 5 gigs. In the future, even higher frequency, okay, gigahertz. And then the 4G network is operated on, I think also several tens gigahertz frequency. All right, so 4G network is operated here. Now, in the backhaul of the 4G network, in the backhaul of the cellular network, where we might have bulk amount of data that we need to transfer, we then use this thing, the terrestrial microwave. There used to be a technology called WiMAX. Okay, it's actually dying, disappearing, at least in Taiwan. It's using a higher frequency range, therefore potentially a higher transmission rate. But this is usually for long haul, sort of close to the core of cellular network type of transmission. The last one, very special, satellite. We don't really use it for everyday, for household purpose, but some of the government and some of the NGOs are using the satellites a lot. Transmission rate can be low and high depending on the frequency range you're allocated for, depending on how much you're willing to pay. But a common characteristic is this: delay, super long, okay? Hundreds of milliseconds. Now, by the way, the optic fibers that are intercontinental or trans-Pacific, transatlantics, they also have long delays. It can sometimes go up to 100 milliseconds. But unlike satellite link, usually satellite transmissions, the only issue is just that the delay is long. Now, satellites, some of them actually are called the geosynchronous satellites because they are actually much higher up around the Earth's orbit, and it's actually rotating with how the Earth is rotating itself. Okay, so it would appear from a person, a Homo sapiens point of view, when we look up into the sky, they seems to be like the sun staying at a certain direction, certain location in the sky. Now, the low altitude satellites, however, is operating in a lower orbit, and it's somewhat more stationary. And so you see that the end-to-end delay for the geosynchronous satellites will be longer, even longer, but the low altitude ones will be shorter. So that was the physical media. All right, so then we are done with the network edge, and let's move on to the network core. So this is what the network core looks like. Okay, again, we have the, sorry, I forgot to do this. Yeah, again, we have this, a network that looks pretty much the internet, but very sort of a microscopic view of the internet. These are the end systems, and we learn now already the access network. What's left is just the core. So if I use one sentence to describe it, the internet core is essentially a mesh of interconnected routers. So all these cylinder here is a router. Good. Now, yeah, this is the physical view of the internet's core. But the question asked is, now, the core here is, playing the role, and a very important role of, transmitting data, switching data around. So potentially a user here or a service here can transmit data seamlessly to another destination. So the transferring mode here, can be designed in multiple ways. The first is called circuit switching. Okay, this was actually how it works for the telephone network. So think of this is necessary as well in the backbone of the telephone network. And that network implements circuit switching. What it does is to dedicate a circuit, a hardware circuit, per call connecting a speaker and the listener. The alternative, packet switching, is used by the internet, where we send data through the network in discrete chunks, or AKA packets. So packets go to the router. Router decide where to go next, and next, and next, and next, almost independently from packet to packet, instead of maintaining a physical hardware circuit to ensure that the speaker and the listener can communicate without any issues. Packets may run into packets and potentially colliding to each other as well. All right, so let's talk a bit more about the circuit switching network. All right, so again, from end to end, speaker to listener, will be allocating resource to reserve and set up a physical call. So at each node in the process, so this call, for example, will be reserving resource on a router, on the link, on the second router, on the second link, the third link, the fourth router, and so on and so forth. We reserve the link bandwidth, we reserve switch capacity or router capacity, so that we make way for the voice that is going to being transferred there. So we have dedicated resource, and this is not being shared across calls. So for example, this segment of the internet here, we see 2 calls, but a part of the switch here reserve resource for call red, and the other for the call blue. So very important, not sharing. So it's a circuit-like behavior. It guarantees very smooth call experience. All right. But you see also one drawback is hey, when the caller here begins a call, there's some time it requires for the network to set up such a physical connection. Okay, so that is called the call setup, and the time requires to do that, that is the call setup time. And that's why when you make a wire phone call or cellular phone call, you dial. The dialing is actually pretty fast. The waiting sound there is also to wait for your friend to respond. But there's a certain delay definitely, and that is called the call setup time. All right. And the way we allocate network resources also come in multiple ways. So it depends on how we divide the whole network resource into pieces. So you see there, in the previous slide, we have a segment of the internet where blue and red will need to share router, share link. But we don't really share resource. That is also saying a particular link, okay, is somehow divided into the resources, divided into small portions, pieces. All right. So usually for a call, a piece is allocated. So the blue call gets allocated a piece. The red call gets also allocated a piece. Okay. Now, when the owner of the allocated piece is not doing anything, then that piece will stay idle. So this can be considered a bit wasteful because it's not being shared. Now, the 2 ways that we are dividing the pieces up are very classic 2 ways: frequency division and time division. Okay, let me explain frequency division first. So let's look at the space of trying to modulate bits, okay, into the medium. So we can modulate bits over time, and there's usually a range of frequencies we could modulate the signal on. So there's a range as well. FDM here, frequency division modulation, okay, works this way. If we have 4 users, then we divide the frequency range into 4 parts, and each is allocated one of the users: blue, green, yellow, and pink. Now, time division is the other way around. So we divide vertically across the time space. And the 4 users are allocated also 4 slots of the time at the time. 4 slots at a round. So 1 round after another. So you see here. Okay. And in a round-robin fashion. So it's fair across the 4 users. Now this is not so bad. You might also ask if there are more users, how do we deal with that? So we could actually divide such that the pieces are finer. For example, the frequency there, the blue channel can be divided further into 2 blue channels. So we could potentially accommodate 8 users, and divide it further, then we can accommodate even more. And let's walk out through an example, and so you get a better idea how resources are allocated in a circuit switch network. So the question here asks, how long does it take to send a file this big from host A to host B, which are on the circuit switch network? And all links runs at this bandwidth, but each link uses the time division multiplexing, time division modulation, and there are 24 slots, okay, per second. Essentially, that cable there is divided into 24 pieces. Okay, so let's begin calculating. So a link has 1.536 megabits per second divided into 24 slots. All right. So each user essentially can only get a 24th of the 1.5. Let's bring up the calculator, shall we? So let's see, how much is that? 1536 kilobits per second dividing 24. All right, so that will be 64 kilobits per second. So essentially, host A and host B there is only allocated 64 kilobits per second of bandwidth for the connection. And we have 640 kilobits that needs to be transmitted. So let's divide that to the 64 kilobits per second. We'll see that it takes 10 seconds. Okay, so it takes 10 seconds just to transmit data. But that's not all, because it says here, it also takes 500 milliseconds to establish the end-to-end circuit. So overall, to complete the transmission, we need 10.5 second time. Right? Yeah, I think you guys also calculate and let me know if you get to you come to the same number. And that was network core using circuit switching. Let's move on to the second fashion. It's called the packet switching. Okay, so people in the packet switch camp actually think very, very differently. They actually think more a socialistic way of sharing resource. All right, so let me elaborate. Each end-to-end data stream is divided into packets. So instead of sending continuous voice, data divided into packets, chunks. Okay. So user A and B will send packets sharing the network resources. Each packet, when it's traversing the link, it's using the full link bandwidth, unlike earlier, right? In the example, we need to divide the full link bandwidth to 24 slots. And the voice cannot use the rest of the full bandwidth. But this time, packet gets transmit real fast using the full link bandwidth. And resources are used as needed, so there's no idle time. If there are packets, packets get sent. It's not like one occupying a certain share of the link. Therefore, even though other people do not have data to send, but they cannot be sending data on the resource. But potentially, using packet switching, we have contention. We kind of aggregate resource demand. And when the aggregated resource demand exceeds the resource, then we'll see congestion. Okay, packets will get queued up. They will have to wait for their turn to be transmitted by the link. So even though each packet gets the full link bandwidth, but when there are more people coming in trying to send, they will all be going on and waiting in line. Unlike previously in the circuit switch network, you need to set up the call. If the call is set up, you get the full bandwidth. There's no such thing as contention. But when there are more people coming and asking for a circuit, if there's not enough resource, those extra demand will be rejected early on. In packet switch network, there's no rejection of using the resource really. So the packets will all be contending. Congestion is the major drawback of the packet switch network. All right. Now, store and forward is a special characteristic of a packet switching network because packet is being transmitted one link at a time and being treated somewhat independently. So the receiver of a packet needs to receive everything before it can determine where to forward it further. So the behaviors of these packets is that a router there receive packets, store the whole thing, and then determine how to forward. So store first and forward. We cannot quite streamline the bits. Okay, in circuit switch network, it is okay. Okay, just go on because there's no contention. You don't need to wait until we store the entire sort of chunk of bits. All right. So let me use an example to explain a bit further what it means by store and forward. Now this is kind of important. Let's spend some time here. We do have a very simple network here. 1, 2, 3 computers. So first one here is the sender. The last one here is the receiver, source, destination. And this guy here is the router, okay, helping forwarding, retransmitting, or relaying data. Now we do have 3 packets, okay, and each packet is this long, L bits. Now you see in the figure, the first packet here being transmitted, arriving partially at the first router, okay, and over a link of R bits per second. Now you can actually calculate how long it takes for packet 1 to get transmitted entirely and arriving here. That will be the size of the packet divided by the link bandwidth, okay. And now because we need to store before we can forward it, so router here need to wait L divided by R seconds until the packet is entirely here. And then spending another L divided by R time to transmit it further. Okay. So by the time the packet 1 arriving at the destination, it's already 2L divided by R. So the end-to-end delay is number of hops multiplying the time to transmit one packet. So let's use an example. Okay, to transmit one hop, if the packet is this big, 7.5 megabits, and the transmission rate 1.5 megabits per second, then it takes 5 seconds to transmit. End-to-end delay, therefore, 10 seconds. Okay, so unfortunately not capable of streamlining the bits over a packet switch network. Potentially transmission delay a bit higher. Now, the next is to describe this characteristic that we might run into contention or congestion inside the network. So what you're seeing here is 2 senders, A and B, sending data out. A here sending green packets, B here sending blue packets. Each of the packet will be using the full link bandwidth to send, full link bandwidth to transmit. But the thing is that, hey, A is just gonna send data as he wish. B here is also gonna just send data as he wish. And all these packets will come to the first router here. Now, if the first router's outgoing link is not fast enough, for example, 1.5 megabits, well, comparing to potentially how A can send data into the first router, right? This is much slower than this. So packets can bunch up over here. So this is where we form queue. And all the packets in queue will need to just wait for their turn. All right. So this thing here, blue packets and green packets mixing irregularly and trying to compete for resource to go on. This is called the statistical multiplexing. So they kind of just mix to each other with not clear pattern. There might be some statistical invariant there, but somewhat chaotic. Okay, that behavior, A and B mixing their packets without fixed pattern, statistical multiplexing. So this is in contrast to TDM or FDM, it looks all very regular. Okay. Yeah, so this is the final example. Why don't we compare packet switching versus circuit switching? Now we finished talking about circuit switching. Now we finished talking about packet switching. So in this example, we do have a sender here. Sorry, I forgot to do this. Yeah, sorry. Yeah. Okay, so end users over here. Okay, and this is the first router. End users will need to be competing to send data over a 1 megabits per second link out. Now, the assumption here is each user will be active sometimes, 10% of the time, but when they're active, they'll be sending data out 100 kilobits per second. Okay. Now, in circuit switching network, how many users can we satisfy? Think. Hey, in circuit switch network, right, we need to set up resource ahead of time to satisfy each user. And the demand is 100 kilobits per second. So 1 megabits per second link can only accommodate 10 users really, even though they will only be active 10% of the time. So 90% of the times, the link here will be in idle. So 10 users, all right, for switching in circuits. Now, in case we are doing packet switching, really nice. Let me just skip the calculation and tell you that we could actually serve more than 10 users here. Okay, if in case we're serving 35 users, 99.996% of the time, these 35 users will be happy. There's not gonna be collision because the probability among the 35 users having 10 of them being active at the same time is very low. All right, so you have 35 users, 10 of them simultaneously accessing 99.9996% of the time. All right, higher than 10 active users simultaneously accessing, really lower than 0.0004% of the time. Well, actually, yeah, lower than 0.04% of the time. Okay, let me put it that way. All right. Now, how do we get 0.0004? Well, you have to recall the probability cores. If we have time, we can try to derive a little bit. What you do is to try to find out the probability of having 1 user being active, 2 users being active, 3, 4, 5, all the way to 10, and then subtract 1 by these. Then you get the probability of having more than 10 active users at the time, being active at the time. All right, and that takes us to quiz time, the quiz number 3, and good that it's just right amount of time for the lecture today. So quiz number 3, okay. So what I'm asking you is to, think a bit more about circuit switching. We see circuit switching is to try to reserve resource and set up physical connections. If I use an analogy, it's almost like building pipes to transfer water. All right. And packet switching is, on the other hand, to try to send data in chunks and then mix and pass over the network in a store-forward nature. So if you think of it, the same analogy as I use for the circuit switch network, it's almost like putting the water in buckets and having people carrying them, passing them on. Okay. So Q1 here asks, which principle do you think the car network follows? So we do have a car network here, right? The transportation system, a human transportation system. So what do you think? How are we transporting cars in our street network? And what about the train network? Yeah, we have all these train tracks there, right? To take trains from places to places. Is train network more like circuit switching or packet switching? Is car network more like circuit switching or packet switching? And last one here. So I'm asking you generally, circuit switching versus the packet switching. Which one do you like better? And do tell me why, okay? And of course, if you tell me that car network is more like packet switching, also tell me why you think car network is more like packet switching. If you think train network is also more like packet switching, tell me why train network is more like packet switching. And that concludes today. I'll see you again live tomorrow morning, starting 10:20. Ciao. And end stream.